equations of motion for 2D rigid body kinetics are Newton's second law, and that says add up all the forces acting on the chosen body. That's equal to the mass of the chosen body times the acceleration of the center of mass. And by the way, okay, so this is the first one. This is not only true for rigid bodies and particles, this is true for general collections of particles or objects. This is true for any collection of particles. So this is true. This is, of these two equations, this is the only one that's true for pudding dynamics. Okay, so, and you're like, what kind of pudding? Like American pudding or English pudding? You know, doesn't matter. General collection. That's pretty cool. Like, so, for example, well, there's a homework problem that asks about this. What if you had 1 million marbles floating out in space, okay? And you applied 50 Newton force to one of those marbles, okay? What's the acceleration of the center of mass of that whole collection of marbles, okay? That's governed by F net is equal to MA. And you're like, well, we don't even know about how close they are. They could be miles apart, or they could, as soon as you apply that force, bounce off of each other or whatever. It doesn't matter. That's the answer no matter what. Okay, that's a surprisingly strong statement we can make about that. And then the second equation of motion is rotational Newton's second law. And that says that add up all the moment vectors about A. That's equal to the mass moment of inertia of the chosen body about A times the angular acceleration vector. That's not true for any A. There's only two possible choices of A. In some cases, there's only one possible location of A. So A is either give me one. Center of mass, that's right. Or fixed, right? In the inertial coordinate system. These equations are only, they only hold for inertial coordinate systems, so I probably could just say coordinate system there. But you can't use these until you represent them in an inertial coordinate system, all of these vectors. All right, so we're going to start using that. I want to say one thing about, so why don't these work for, why can't we use this approach for 3D rigid body kinetics? The answer is, okay, so I'm going to draw what happens generally in 2D and draw what happens in 3D and show you the difference. Okay, so in 2D, let's say that we have 2x4, big board that's moving in space. And I'm going to draw it at two different instants. Here's instant one. There's instant one. I haven't drawn anything yet. That would be super creepy. Okay, so at instant one, this board is in this position. And our coordinate system is this with the z-axis pointing out. Okay. And at instant two, this board has moved to a new orientation. There's the coordinate system. In 2 dimensions, all rotations are about the z-axis, right? So the only moment of inertia that matters is about z. Anybody have any questions about that? Does that make sense? And notice that in any orientation of that board, the moment of inertia of that board is the same. Okay? Rotating it doesn't change the mass moment of inertia. Both instants, IA about Z is the same. Okay? So IA is constant in time. Right? Now let's draw what happens in 3D. Again, instant 1 and instant 2. And I'll do sort of the same thing again. We have this board. At instant 1, it's in that orientation. In instant 2, it's in this orientation. And now I'll draw the coordinate system. There's X, Y, and just be clear about Z. And here's X, Y, Z. Okay. So at instant 1 and instant 2, the mass moment of inertia is about Z are the same. But think about the mass moment of inertia about the x-axis. Here, if you think of this as like a slender rod, in this case, it's a slender rod, and you calculate that as 1/12 times the mass times the length squared. Here, it's doing like a barrel roll about the x-axis, and you'd have that, that sort of trivial case where I said we never actually use that, but here the mass moment of inertia would be 0. Okay, you see that it's because of the rotation about the z-axis, the mass moment of inertia about x changed. And the same is true about y. Here we have a barrel roll about y, and here we have a tumbling thing of this rod. So the key thing is, but Ix and Iy changed. So in general, in other words, the mass moment of inertia in 3D changes in time. Okay, so that's a fundamental difference between 2D and 3D. In 2D, you have this idea of a mass moment of inertia that's constant. In 3D, you don't have that same thing, and so you have to treat it totally differently mathematically, right? Uh, that's just sort of background information. That's not really going to come up in problems in any way. If we have enough time at the end, I don't think we probably will, but sometimes I do a little section on how you would approach 3D rigid body problems, and it's sort of cool. Mostly it's horrifying to see like how much more complicated it gets to do these calculations in 3D. And because of that, people don't even tend to do 3D rigid body problems using Newton's laws. They tend to do it using an energy minimization kind of approach. Any questions? Okay, now I'm going to give you a general set of steps that we're going to do. We're going to I'm going to try to remember to follow in my examples. It's not the only set of steps that'll work, but it'll always make sure you get everything done. So a lot of people like to have a set of steps like this. Okay, so here's a general set of steps for 2D rigid body kinetics. So first, ask yourself, for the rigid body you're dealing with, does this body have a fixed point? Is there a point on this body that's fixed in your inertial coordinate system? If yes, then that's going to be your about point. That's the about point A. If no, the center of mass is the about point. You could do every problem with the about point at the center of mass, even if there's a fixed point. And I think at some point I'll do an example where you see how it works in each of those two cases and you get the same answer. But you'll be adding a lot more time to those kind of problems. So I think you'll definitely prefer to choose the fixed point if you have it. Second, now that we've chosen the about point, calculate the mass moment of inertia. Third, draw a free body diagram. And this is required, even if you don't think it's important, then you can stop doing it as soon as this class is over. But anytime you use Newton's laws in this class, you need a free body diagram. Fourth, determine all forces and moments. Well, I guess that's sort of part of the free body diagram, but do it mathematically. So how many non-zero components are we going to get for our force vectors? 2. Yep. Or you like Peace Bro. Yeah. So this is 2 components. And how many non-zero moment components are we going to get? One. And why is that? Well, there's probably a lot of answers to that, but because we're only doing 2D problems. Okay. If we were doing 3D problems, the answers here would be 3 and 3. And this is where I write out the rho, the force, and the moments in a table. Okay, now step 5. We're only going to do if the about point is the center of mass. Is Newton's second law. So F net is equal to mass times the acceleration of the center of mass. How many useful equations do we get from this? 2, yep. And then step 6, we're always going to do. What do you think that's going to be? Not yet, but that is going to be sort of, I'll mention that next. Moment, yep. So rotational Newton's second law. This we're going to do in every problem, no matter what the about point is. So sum of the moments is equal to the mass moment of inertia about A times the angular acceleration. How many useful equations are we going to get out of this? 1. And then this you can think of as the constraint equation, if needed. Then you'll calculate the acceleration of some point on the body as the acceleration of the point relative to, well, just write it like this. So if we're trying to calculate the acceleration at some point that other than the about point, watermelon equation and or relative motion equation. Okay, so you don't have to follow this exact order of steps. If you like to just sort of feel and think your way through, that's fine. But if you follow this set of steps, you'll never forget anything. So that's sort of a plus. Yeah. The acceleration of the center of mass in the case. So if your about point is the center of mass, that means there's no fixed point. We're talking about like things flying through space or whatever. And so if you add up all the forces, that'll let you relate the forces to the acceleration of the center of mass, the acceleration of your about point. Okay. That'll let you calculate center of mass relative to ground. Okay. All right, so now we're going to do, oh no, first I'm going to do a few boring examples. We're going to get into some cool examples now. Okay, so first example. So let's say we have a hinge connecting a bar to a wall. And let's say that the length of the bar is 2 meters. The mass of the bar is 10 kilograms. At the instant shown, this bar is released from rest. What's the acceleration of the point P at the end of the bar? Okay, well, let's just go through the set of steps. Does this body have a fixed point? Yes, so the about point is at the hinge. And so now we're going to calculate the mass moment of inertia at the hinge. Since the hinge isn't the center of mass, we're going to have to use the parallel axis theorem. So this is going to be equal to the mass moment of inertia about the center of mass plus md squared. If you look at the table for mass moments of inertia, I didn't give a this, so you can assume that we're treating this as a slender rod. The formula is 1/12 times the mass times the length squared. And now we're displacing our about point from the center of mass to where the hinge is. So we're going to add the mass of the bar times d squared. What's d in this case? 1, exactly. It's the distance from the center of mass to the about point. So 1 squared. And let's see, what do we get here? So that's 33 and 0.3 repeating plus 10, right? So, no. 0.3 repeating plus 10. So 13.3 repeating. What are the units of mass moment of inertia in SI units? Kilogram meter squared. Step 3, free body diagram. Okay, so what forces do we have acting? There's a weight force, and we can always treat that as acting at the center of mass. The weight is 10 kilograms times 9.81 meters per second squared. So 98.1 newtons down. And now the only other forces we're going to get is contact forces. So imagine going around the boundary looking for contact with the surroundings. The only other place is at the hinge. And what kind of loads does a pin joint apply to a connected body? So no moment. So in 2 dimensions, a body that's not connected to anything can do 3 things. It has 3 degrees of freedom. Okay, it can translate in x and y. Okay, or any combination of those, and it can rotate about z. Okay, so it starts with 3 degrees of freedom, and then the joints take those degrees of freedom away. So forget about everything else. Does this joint restrict, does it prevent motion along the x-axis? Yes, so there's definitely going to be an x component of force. Does it restrict motion, prevent motion along the y-axis? Yep. And so there's going to be x and y components of force. Okay. Does it prevent rotation about the z-axis? No, so there's no couple. And so pin joints produce a vector of unknown force components. Okay, so that's 3. Now 4, I'm going to write out this table. We're going to, each of these forces, we're going to calculate the rho vector, the force vector, and the moment vector. Our about point, we already chose at the fixed point. So this is A. Yep. Then, then there's no dynamics, like calculating the acceleration is, there'd be no acceleration. And, so we can have rollers and stuff, and then we have to deal with the kind of loads but we can't ever have fixed joints in dynamics, or the dynamics are very boring. If you have a fixed joint, then you're doing statics, Okay, so let's first deal with R. What's the rho vector? The vector from the about point to where that force is applied? 0. The force vector is Rx, Ry. Cross product, all we care about is the z component, and you get 0 for that. And now we'll go to the weight force. What's the rho vector? 1, 0. The force vector is 0, negative 98.1. And the cross product then is negative 98.1. Does it make sense that that weight force would produce a negative moment? Yeah, it would cause a clockwise rotation, which is negative, so that's right. Step 5. If the about point is the center of mass, then you use it. Here, the about point is a fixed point, so we're not going to use Newton's second law, at least not yet. Maybe later it'll come up. Step 6 is rotational Newton's second law. And for that one, we're going to add up all the moments. That's just, 0 minus 98.1. And that's equal to the mass moment of inertia, 13.3 repeating, times the angular acceleration. And so we can calculate alpha. And it's equal to negative 7.38 radians per second squared. Angular acceleration is really a vector, but in 2D, all of our vectors are all of our, any vector that represents a rotational quantity has only a z component. So if you wanted to write this as an angular acceleration vector, it would be 0, 0, negative 7.38. Okay. And now we're to step 7, which is just basically, now we're out of the Newton's laws and just trying to apply what we learned to calculate what we're asked for. Okay, so let's think again about what we're being asked for. So we have a bar like this with a length of 2 meters, and we're trying to calculate the acceleration of this point here. And any point that's moving on a rigid body that's rotating around a fixed point is in circular motion around that fixed point. Okay. So the acceleration of p, this is p, is equal to alpha cross r plus omega cross the quantity omega cross r. And now we're just filling in those values. Alpha is what we went through all of Newton's laws to calculate. That's 0, 0, negative 7.38. R is the vector from the center of the circular motion to the point we care about. So what's that vector? 2, 0, 0. And what's omega? 0, that's right. So I said at the beginning that we're releasing this from rest. So at that instant, it doesn't have, none of the points have any velocity yet, and the body doesn't have any angular velocity. So this is just 0. And now we can put this into the watermelon equation, and we have 0, 0, negative 7.38 crossed with 2, 0, 0 plus this stuff all goes away because omega is 0. And we get 0, negative 14.76, 0.